Okay, so welcome to lecture 20. And yesterday we were doing derivation of linear momentum balance equation, LMB, for deformable bodies. Okay, and we had the following integral form. It is also called global in nature. So the first term is an integration over the current region of the part of the body, that is dt. Okay, so we are writing this for a part of the body, right? Then the second term corresponds to traction forces, and therefore it is over the surface of the dt. And this traction is a function of y, t, and also the normal. Okay, this body force B is just a function of y and t. Okay, it's not a function of normal because there is no normal. It's inside the volume, right? There is no surface there. And this is the total external load, and it has to be equal to rate of change of linear momentum of this part of the body, right? Which we wrote as d by dt of integration over the volume dt, and we had rho bar v bar dvy. Okay. All right, so see, we want to derive what is called local form of linear momentum balance, a differential equation which would hold at every point in the body. Right now, this is not a differential equation which holds at every point. It's kind of global in nature. Okay, so let's try to derive that differential form. So, one of the things should be that why don't we convert all the terms here into volume integral? And then we say that since it's holding for every volume dt, therefore the integrand must vanish. Right, that is called the localization argument. So our first task is to convert surface integral into volume integral. Then push d by dt inside the volume integral on RHS. And finally, use what is called localization argument to say that the integrand of the volume integral must be 0. Okay, that is called localization argument. Because you are trying to localize it, no? From integral, you are going to a local point. So let us do these steps one by one. The first one obviously is the surface integral conversion to volume integral. And can you guys think of what should we do here? How is surface to volume integral done? Yes, anyone? How can we achieve that? Cost avoidance theorem, right? So this is what we have to do. And you see that right now it's a surface integral, And if you recall the Gauss divergence theorem, the standard form of Gauss divergence theorem is that integral over the volume dt of divergence of a vector field, let us say some vector field xi, okay, and dv, this is equal to surface integral xi dot n day, right? That's the Gauss divergence theorem, and we want to use that here. So right now, this surface integral doesn't look like in the form that we have over there. So we have there a vector field xi, which has to be dotted with the normal n. So Chaitanya is asking, can't we apply integral form to every point in the domain? Yes, you can apply that, but it won't give you anything because one of the terms is a surface integral. Everyone must be volume integral, no? Okay, so you see that it's not in the standard form, this surface integral, integration of traction. So that is where we introduce this formula for traction, that is sigma times n, okay? And then we have del dt sigma times n day. But it is still in the form that we want. It is still not, because look at the Gauss divergence theorem, the surface integral has got vector field dotted with the normal. And here we have a second order tensor multiplied with the normal n. Okay, so it's not in the form that we want. So what we are going to do is we will do a trick. So let's multiply this thing with a constant vector c. Okay, c is a constant vector. All right, so if we do that, since it's a constant, we can bring it inside the integral, and then we have del dt sigma n dot with c day. Okay, and we can further write it as integral over del dt sigma transpose c dot with n day. Can you do that? Because you see, the second order tensor, when you bring it on the other side of dot product, it becomes a transpose, right? So that is what we have here. And now you see this thing inside the bracket. This is like this vector field xi. So it is now in the standard form, which we can now use. And I mean, we can apply Gauss divergence theorem. So let us apply Gauss divergence theorem here, GD, and this will then give us volume integral dt, and then we have divergence, okay, and this is divergence y dotted with sigma transpose c day. Okay, so we have been able to apply Gauss divergence theorem and convert this into volume integral. But see, this is not what we wanted. We want the formula for this thing over here inside the bracket. So somehow from this term over here, we have to take c outside. Okay, so how can we take c outside? That is the question now. Can someone think of how to take this c, the constant c, outside? So of course it is not so trivial. So what we can do is, whenever we are stuck like this, we switch to indicial notation and then try to see what can be done. See, you can't take sigma on the other side here. Somebody is saying sigma, take sigma on the other side. You can't do that because you have an operator divergence here. If you take sigma outside, then there will be no derivative on sigma, but right now there is some derivative on sigma. Yeah, so Toiba is asking, is it dvy or dy? So you are very true that it is dvy, it's a volume integral. Okay, so we can't do that, but let us convert this into indicial notation. So here we have, let us say, xi equal to sigma transpose C. Then what will be xi I, the ith component? Can we say that this is same as sigma ji cj? Isn't it? So ith component of xi is sigma ji cj. See, it is not sigma ij cj because it's the sigma transpose. So it is sigma ji cj. Okay. So sigma is the Cauchy stress tensor. And don't think that sigma is equal to sigma transpose. It is going to be, but for right now, we haven't found out that sigma is equal to sigma transpose. We just know that there is some stress tensor sigma, Cauchy stress tensor sigma. The symmetry will prove later on, but for the current proof, we can't use that. Anyway, so this is xi I. Then what will be divergence? So what is then divergence of xi? Isn't it del xi I over del yi? So that means this is same as del over del yi of sigma ji cj, right? So we can put it here now. So this is integral over dt del over del yi sigma ji cj dvy. Okay. Now you see that cj is a constant. So when you take the derivative with respect to yi, it is, no, there won't be any derivative. It will become 0. So you can also say that this is same as integration over dt del over del yi sigma ji cj, and cj, c is a constant, right? So let me keep it right now here, dvy. So this is really interesting right now. We have to think of what is this thing over here now. I want to go back to tensor form, okay? I want to go back to tensor form. Can somebody think of how to do that? It is some kind of divergence of stress tensor. Let me show you, first of all, the indicial form of divergence of sigma. Okay, so I'm doing divergence of second order tensor sigma. Let's try to find out its indicial form. Can I write this as divergence y dot sigma ij, and actually to be, you know to make it more resembling with what we have, I'll say it is sigma ji ej tensor product ei. Okay, that's the stress tensor sigma, no, just written down expanded in an expanded form. Sigma is sigma ji ej tensor product ei, and I want to take its divergence. So you must be knowing the indicial form of this divergence. So what we have to do is we do del over del yk sigma ji ej tensor product ei, and then there's a dot with ek. That's the formula for divergence, okay, from your mathematics. Now take the derivative with respect to yk. So what we have is del sigma ji over del yk ej tensor product ei, and this is now dotted with ek. And the way this dot is done is these two have to be dotted. Right? That is how a second order tensor is dotted with a first order tensor. So this then becomes del sigma ji over del yk ej delta ik. Okay, remember this, you can always use this formula for divergence, and it can be applied to first order tensor, second order tensor, third order tensor, fourth order, of any order. Okay, and you see when I take the derivative with respect to yk here, ej and ei are constant, so there is no derivative on them. Therefore, the derivative comes only on the component of sigma. Anyway, so this is what I have, and finally, this being a Kronecker delta function, the k will change to I. Okay, so this becomes del sigma ji over del yi ej. So that's divergence of sigma, and remember, divergence reduces the order of the tensor. Therefore, we started with a divergence of a second order tensor, and what we have finally is a first order tensor. It's a vector. Okay, so that's your divergence of sigma. But what do you think this dotted with C is going to be? So this is, just write down whatever we have till now, del sigma ji over del yi ej, and this is then dotted with C. So what is this then? ej dot C is simply Cj, right? When you dot these two vectors, C dot ej will give you Cj, the component of C along ej. And therefore this becomes del sigma ji over del yi into Cj. Okay, and isn't this what you have over here? So this thing that you found out, isn't this what you have over here? Right? So this switching from indicial and back to tensor has been able to tell us that the tensor form of this thing here is this particular tensor. Okay, so we can now write this as volume integral dt divergence with respect to y dot sigma dot with C dvy, isn't it? So see, we are able to go back to tensor form. And then when you compare these two, you see now you can take C outside, right? Because C is a constant, you take C outside. So the last step is obviously that you write this as volume integral divergence of sigma dvy, and then the whole thing is dotted with C. Okay, so you can now compare these two, what you started with and what has you gotten finally. If you compare them, then what you have derived is actually the Gauss divergence theorem for second order tensors, and it is that sigma and day over the surface, that's equal to volume integral divergence of sigma dvy. Okay, so final result looks quite similar to what it was for vectors. So on the left you have second order tensor multiplied with normal, and on the right you have just the divergence of the second order tensor. Okay, so anyway, so doing this exercise was also helpful for us to see how to work with indecimal notation and how to get back to tensor form. Okay, so we have worked out the conversion of surface integral to volume integral. First point is done here, and this is, we have written it as volume integral dt divergence of sigma dvy. What is now required is the second point here. We have to push d by dt inside. Okay, so let's try to do that now. Now that is really tricky, and I'll show you in several ways. So what we have is rho bar, v bar, and dvy. So that's a total linear momentum, and I want to take its d by dt. And understand that the domain is changing with time. So to bring this d by dt inside, we have to kind of change the domain, isn't it? We have to apply some kind of chain rule to switch from dt to the referential domain d, isn't it? D ref, the referential region of the part of the body that we are looking at. If we can do that, then we can very simply bring this d by dt inside, isn't it? Yes, it's a triple integration. Thank you. So let us try to do that. So you have this. So see, it is quite simple. So you have rho bar, and then this y, you will have y hat as a function of x comma t, and v bar. Okay, this was v, is also like that only, y hat as a function of x comma t, and times, you can say j, which is a function of x comma t, right? And then you have dvx, and then this converts to d ref, isn't it? And then you have d by dt. So this is simple chain rule. So I'll say, so is it called chain rule? Well, I think I should say change of variable. Yes, it's a change of variable. Okay, is everybody with me till now? And you can see that now the domain is not a function of time, so you can very simply bring it inside. Okay, so this then becomes d ref, and you have d dt of this whole thing, rho v j dvx. Okay, now I somehow want to go back to dt, because I can't work with d ref here, because you see the other two terms over here, they are in dt. So I want to have everything in dt. Okay, so now I'm going to kind of apply product rule. So this is then going to be integration over d ref d dt of rho bar v bar into j plus then you have rho bar v bar j dot, okay, dvx, and understand that these dots are material time derivative. Okay, so you take the time derivative while keeping the particle fixed. That's the material time derivative or Lagrangian time derivative, right? So okay, then what should we do? It's really getting messy. So j dot, we know that this is j times divergence of velocity, isn't it? So that's not difficult. So okay, if we do that, then we have it's simply d ref and ddt of rho bar v bar with this velocity vector plus rho v, okay, rho v times divergence of v. It's divergence of v and it's really getting difficult, times j dvx. Okay, so, but now you see that this j dvx, it's equivalent to dvy, right? And this allows you to convert back to dt, the current domain. I hope that all of you are with me. We are just doing some maths, but it's very important. So you can't neglect this. Mathematics is very important because when you guys work out, if you do some research later on, you will have to derive new equations. And you can't do that without knowing some of the basic derivations. Or for master students, when you do a project, it will be very important. And it's also important for understanding purpose. I'll show you, I'll get something that you'll very much appreciate. So this is then equal to, we are switching back to current domain dt, and inside we have d dt of rho v plus rho v divergence of v, okay, dvy. Okay, the next thing, I'm also going to apply product rule here. So what is this going to give you then? So we have integration over dt, and this then becomes, let's see what we can say. Yeah, I mean, it is quite simple, no? It is d dt of rho times velocity plus rho. I'll write this term first, plus, well, let me write it the way I was going on, plus rho bar into v bar dot, okay, and a super dot means it's the time derivative, okay, material time derivative. So everywhere, let's keep it that way. So we have rho bar dot, okay. So nobody's asking me question. I hope you guys are following me. Plus rho bar v bar divergence of velocity dvy. So this, you can also write it as rho bar dot plus rho divergence of velocity multiplied with velocity plus rho v okay times dvy. And actually, you see, what is this thing here? V dot. What is V dot? Although it's the Eulerian velocity, but Eulerian velocity is same as Lagrangian velocity, and you have to take the material time derivative. So what will be V dot? Acceleration, right? So this is, we can write it as acceleration. And you see the first two terms. Why I have written like that? Because if you remember, this thing inside the bracket is the Eulerian form of mass continuity equation. This is supposed to be equal to 0, isn't it? So you can simply say, why don't you go away? And then we have integral over dt rho times acceleration dvy. Okay. So you see, we started with something which was very simple, what we started with. Along the way, it became quite messy, right? But finally, it again became quite simple. And the whole thing appears as if you simply bring this d by dt inside and just take the time derivative on v. Isn't it? It appears like that. But as you can see, if somebody does that naively, that is obviously not correct, isn't it? There is, of course, another way to derive the same thing. Let me try to do that. There is another way to derive the same thing. And I'm going to show that here in a different color, let us say in black. So this thing you can also write, the first thing is the same as earlier. You convert this into referential domain, d ref, and then you have rho bar, v bar, j, t, v, y, okay? And then you also write it as ddt, t ref, and you see this rho bar times j. So that from the Lagrangian form of mass continuity, what is rho bar times j? Isn't that rho naught of just x? Remember rho naught, the referential mass density, that's rho naught times velocity into dv. Okay, this is dvx, by the way, into dvx. And now you can see that indeed when you bring d by dt inside, it's only going to act on velocity, because rho naught is not a function of x. So sorry, rho naught is not a function of time. Okay, and therefore you can write this as triple integral d ref rho naught as a function of x and d dt of velocity. It's the material time derivative. It's going to give you acceleration. Okay, dvx. And finally, you can switch back to, if you want to switch back to dt, then you also write this as dref and rewrite rho naught as rho bar, okay, into acceleration into j dvx, and this then becomes integration over dt of rho bar a dvy. Okay, I hope that this is clear to everyone. So this was a simpler derivation, but of course I also wanted you to see the other one, the bigger one. Both required use of mass continuity equation. One was over here in setting it equal to 0, and the other one was over here in saying that rho into j is equal to rho naught. Okay, so once we have seen this, now we can go back to our original equations. So this thing is simply integration over dt rho bar acceleration a bar dvy. Okay, now the whole thing is indeed an integration over just dt. So you can bring all of them together and it simply becomes you have a simple integration over dt, single integration, divergence of sigma plus body force B minus rho times acceleration, and this thing is equal to 0. Okay, the integral form. Okay, but now the integral form is such that all the domains are dt and there is no time derivative outside. And now you use the localization argument. So from here, we will use localization argument because this holds for every dt. See, because it is going to hold for every dt. So we can say that divergence of sigma plus body force is equal to density times acceleration. And this is what is called the Eulerian form of linear momentum balance. Okay, and it's a tensor form. It's in the tensor form. You can also think of writing this in component form. All right, so if you want to do it in the component form, then you first have to write down divergence of sigma, and you have already seen that what is divergence of sigma. So look here, that divergence of sigma is this thing over here, del sigma gi over del yi ej. So let me write that over here, del sigma ji over del yi ej plus you can say bj ej is equal to rho bar into aj ej, and then extract the ej component from everywhere, and this gives you the component form of the linear momentum balance. And you can be more explicit now. So you'll say del sigma 1 over del y1 plus del sigma 1 2 over del y2 plus del sigma 1 3 over del y3 plus b1, that's equal to rho times acceleration 1. So this is for j equal to 1. Then you likewise think of j equal to 2, and it is del sigma 2 1 over del y1 plus del sigma 2 2 over del y2 plus del sigma 2 3 over del y3 plus b2 is equal to rho times acceleration, and finally del sigma 3 1 over del y1 plus del sigma 3 2 over del y2 plus del sigma 3 3 over del y3 plus b3, that's equal to rho times third component of acceleration. Okay, so this is the component form fully expanded, whereas over here a very compact tensor form. Which one do you like? I'm sure you like the compact form, but of course it is kind of not telling you what exactly it is. The component form is telling you very clearly, okay, you have these components and you have to take the derivatives, where the tensor form is kind of abstract, but in a compact form. Okay, had you guys seen this component form of equation earlier? You must have seen this, no, in undergraduate class. Yeah, and if you have, if you recall, if you just turn back, if you have, kept your notes, you will see that when you derived it, you had done so many approximations. Whereas right now, our derivation is exact. We have not applied any approximation and derived the same equation. Okay, so this is the linear momentum balance equation for deformable body. So force equal to mass times acceleration plus for a particle. It's now this for the deformable body. Any questions so far? Yeah, Toiva is asking, sir, I might have missed, but what is localization argument? Okay. So, when you're going from this dt and saying that the integrand is 0. So basically, because it holds for every dt, right? It holds for every dt. So you can say that integrand is 0. And by doing that, you are coming from what is called the global form of equation to local form of equation. So this is the local form of equation because it holds for every y. It holds for every point in the body. Whereas this global form, it is for the entire body together, right? An entire part of the body together. So because you are able to derive a local form of equation, therefore we call it localization argument. I also would like to bring to you another form of this derivation that we did here. So to do that, and this is related to, some people were asking question yesterday, why we can't use, why we can't apply their LMB to just for to system whose mass is also changing. Some people were asking this question yesterday. So let me try to answer that question by doing some derivation. Basically I'm trying to, derive the Reynolds transport theorem, and that will kind of help you. So my starting point would be from, let us say from here. Okay, maybe from here. Yeah. So what we saw is that integration over d dt, and then we had dt of the total linear momentum rho v dvy. This is same as integration over the same volume dt, and then you have rho v dot plus this thing over here, rho v divergence of velocity and and then this whole thing is then multiplied with dvy, right? This is something we have already derived earlier. And then what we are going to do is we will also write it as integration over dt, but then we say it is simply del over del t of rho v. So obviously we'll have a convective term also, right? So this del over del t is like the Eulerian time derivative, keeping y fixed, and so you will have divergence of rho v, which is actually a second order tensor, multiplied by the velocity itself. Okay, as you have already seen this thing, right? For any tensor, this is how you can convert from, how you can relate the Lagrangian time derivative to Eulerian time derivative. And then you have this extra term, rho v divergence of velocity. Okay, and this thing is then multiplied with dvy, but this is also same as integration over dt del over del t of rho v, okay, plus, of course, to see this you have to again do it through indicial notation, but I will directly write down the result, that this is same as divergence of rho v tensor product v. So the thing above, the two terms is same as divergence of rho v tensor product v. Maybe you guys should try to work this out and see. Let's work it out in indicial notation and show that both give you the same indicial form. Okay, you should try to do that. So this times dvy, and then this is then equal to integration over finally dt del over del t of rho v plus the other one for dt divergence of the second order tensor. But we had just derived how to relate, how to use Gauss divergence theorem with a second order tensor. And then you can see that this is then going to become integration over dt del over del t rho v plus and then this dt is going to convert to del t, surface integration, del of dt. And this is then going to become rho v tensor product v multiplied with normal n dvy. But then you also know that this is integration of dt del over del t of rho v plus the surface integral del dt rho v into v dot n d, sorry, this is day, this is day. Okay, now I think you guys can actually see what is the second term here denoting. People from fluid mechanics would actually be able to relate it very easily. What is the second term here? Remember that this is the d dt of this dt here right? Still from fluid mechanics. Can you tell me what is this last term on the right hand side denoting? Yes, that's a momentum flux. The momentum flux coming out of the surface of the control volume. Isn't this something that you would say? So dt is like the control volume. So what you see is that the actual, what is on the left hand side is actually sum of two terms. If you know, because many times people in fluid mechanics look at just a control volume. So if you are looking at a control volume which is fixed in space, then that doesn't mean that you have the same set of particles, right? Because for a control volume fixed in space, let me also draw a picture. So suppose this is a fluid flowing, and it can be fluid as well as solid, okay? And then you have this control volume. So you have this control volume which is fixed, okay? Fixed control volume. So what you see is that fluid particles are not just entering but also going out. So mass of the system inside the control volume is not the same at every time. So I can say that we don't have same set of particles inside control volume at every time. Now, of course, if you are doing the left hand side, that means you are kind of tracking how the system is evolving, how dt is changing. Then you're perfectly fine and you have just one term. But if you want to calculate the rate of change of linear momentum through control volume approach, then you come to the right hand side and the first term, so in place of dt, you'll have this control volume, whatever is the fixed control volume, and then you have two terms here. You can't just calculate the rate of change of linear momentum of control volume. So the first term is simply the rate of change of linear momentum of control volume. And the second term is the momentum flux through the control volume. And the two terms together gives you rate of change of linear momentum of the system. Okay, so when you apply Newton's second law, if you think that I'll apply Newton's second law to this control volume, and then don't make this mistake. So if you think of applying Newton's second law to control volume, see what you'll get. So you'll say rate of change of linear momentum of control volume, right? And this will equate it to total external force, right? This will be Newton's second law, isn't it? But what is the rate of change of linear momentum of control volume? That's just the first term that you had over there. So it's integral over the control volume, then del T of rho V dVy. This is it. This is the rate of change of linear momentum of control volume. And this you are equating it to the external total external force, which will have two terms, the body force term and then the surface term, like I say del CV T TA Y. But then you see that this is not correct, because when we worked out using control mass, then this was equated to two terms. One is this thing, rate of change of control volume, and also this flux. This also has to be there. Okay, so this is something you are missing here. So I can say that flux part is missing from the left hand side. So this is not correct. So you thought that, okay, apply linear momentum balance to control volume, rate of change of linear momentum control volume. It is just this term on the left hand side. You get it to total force on the control volume. You get a wrong result, because you can apply linear momentum balance only to control mass, not to control volume.
So for deriving the Reynolds transport theorem, we can directly start from the end result, like rho times acceleration into dvy, and split acceleration into a special time derivative and material time
But you
derivative.
see, how did you know that it is rho times acceleration dvy?
Yes, we have to proceed. Okay.
I mean, rate of change of linear momentum of a system, how did you know that it is rho times a of dvy? It is okay for a particle, single particle, that it is mass times acceleration. But here you are not having, you have to first identify a system, right? Then only you can apply Newton's second law.
Yes, sir. But what I'm saying, once we have this end result, the
No,
derivation we have.
this is like cheating then, right? You will say that, okay, I have the end result, then I know that this is Reynolds transport theorem. It has two terms. So when I'm applying it to control volume, I'll make sure that I also keep the momentum flux term. But when I apply it to control mass, then I don't need to have the momentum flux term. So of course, if you are differentiating that way, then you can apply linear momentum balance. But what I meant is, usually what is Newton's second law? That net external force is equal to rate of change of linear momentum of the system, right? That's the Newton's second law. Now, if you choose your system to be control volume, whose mass is changing with time, then you see the rate of change of linear momentum of the control volume is simply one term, right? And you equate it to total force. So it won't give you correct result, because you know that the correct result has got two terms, right? The momentum flux should also be there. So this is what I meant when I said that you can't apply Newton's second law to a system whose mass is changing with time.
Sir, when we talk of fluids, so
Yes.
acceleration in any flow system or in any control volume system is has two components, right? One is special and one is
Right.
material time derivative.
Convective acceleration.
Convective acceleration and special acceleration.
Convective and convective.
Yes. Okay. From there also we can draw an inference.
What inference you want to draw from there?
This one only, sir. Like we have discussed now, there will
Okay,
be.
I mean, are you okay with my query that, I mean, my comment that you can't apply Newton's second law to a system whose mass is changing? Or you still have some doubt about that?
No, sir, there's no doubt.
But then what you're saying, I'm not able to understand what you're trying to relate to.
No, sir, I'm saying the same thing. Like,
Okay. So yeah, I understand that what you're saying is that when you do del t of this thing over here, it is not giving you acceleration. It is simply the Eulerian time derivative, so it is not giving acceleration. I think that is what you're saying.
yes, sir.
Okay. But this is the rate of change of linear momentum of control volume. This is, you'll agree with, right? This is indeed the rate of change of linear momentum of control volume.
Yes, sir. Yes. Right.